Thanks, Virginia. Okay, thank you. So I'm sure anyway here you all saw at least one bird flying off into the distance to who knows where. It's just what they do. It's how they get around, and it's so important to their everyday lives. That's why understanding how they fly and their flight style is so important to their ecology. However, it's quite easy to do this in modern birds. I mean, you just need to look up, right? But in fossil birds, well, good luck telling me anything about flight style based on that. So this is where we have to be a little bit more inventive. And this is where these come in. So this is an aerodynamic power curve, or APC for short. And all it shows you is the amount of power that a specific flying individual needs in order to fly at a certain speed, with the different interactions of drag creating a U-shaped curve. If we then add on top of this the amount of power that the bird's actual flight muscles can produce, or the AP max, we can then begin to say some things about flight style. So for this presentation, the most important thing that we can get out of this is whether or not the bird can actually fly or not. Because while the bird can produce enough power to fly at speeds below this maximum producible power line, it can't actually produce enough power to fly at speeds above the line. So if the APC falls entirely above the AP max, the bird can't fly at all. Simple as. So let's take a look at a modern example in order to hammer this home. So everyone is familiar with swans. Very pretty birds, occasionally try to steal your sandwich, those ones. So this is the APC that I created earlier for a particular specimen of a mute swan. As I said before, the bird can produce enough power to fly at speeds anywhere below this maximum producible power line, so in this area here. And that means that it can fly anywhere at speeds in between this range, which is anywhere between 14 kilometers per hour all the way up to 79 kilometers per hour. Now, this is actually quite representative of real life. So in order to fly, a swan needs a run-up. It can't just jump up into the air and fly off like a pigeon. And they have been known to actually keep up with cars. So there is more that we can say from this graph, but suffice to say that it is actually representative of real life. So we can see how this would be useful when looking at fossil birds. However, in order to calculate power, we need three measurements: body mass, the surface area of the body, or body frontal area, and the surface area of the wings, or wing area. And again, good luck getting me those measurements based on that. So this is where we have to be, again, a little bit more inventive. Well, a little bit more inventive. So we get around this by using regression equations. Now, these are created using modern bird data, for which we can actually measure body mass, body frontal area, and wing area. These are our desired variables. If we then pit these against variables that we can actually measure in the fossil data, such as bone lengths, then we can get a predictive equation. We can then use this predictive equation to actually estimate our morphological variables and then calculate power and create our APCs. However, again, this is where our issues begin. See, our issues begin here because we have no choice but to use modern bird data. And as we all know, modern birds, fossil birds do not necessarily have a modern analog. It's the same for all fossils. So we're using data that's not necessarily representative of the fossils in order to estimate morphological variables for the fossils. Is it just me, or is there something clearly flawed here? So there's clearly going to be some error introduced here, and we need to actually estimate what that error is. And the best way to do that with regression equations is by looking at their confidence intervals and their prediction intervals. So let's start with confidence intervals, something that I hope everyone is familiar with. So confidence intervals show you how representative the mean of your sample, or your blue regression line, is to the mean of the entire population. They show your regression equation's repeatability, or its precision. However, we don't actually care about precision in this case. Now that's because, as I said before, fossil birds don't necessarily have a modern analog. So that means that we don't actually care about the mean of modern birds. The true value of our fossil birds might actually lie here, or here, or here, or basically anywhere except for near that blue line. So we definitely don't need confidence intervals. What we need are prediction intervals. Now, prediction intervals are wider than confidence intervals, and that's because they encapsulate 95% of the data points within our sample, and not just the mean. This means that if we've created our data set well enough, then this should be representative of the entire population of birds, and just maybe, they might actually cover where the true values of the fossil birds lie. They show our regression equations' accuracy, or how representative the data set is of the entire population. So we're already increasing the amount of error in our APCs by having to use prediction intervals instead of confidence intervals. However, that's not the only source of error that we have. So this is the power equation that you have to use to create an APC. And what I want to draw your attention to is the fact that body mass is squared, and then both body frontal area and wing area are then added on top of this. that means that the error from multiple different elements are being combined into one equation, and this is a phenomenon known as error propagation. Now, error propagation has its own specific set of rules to follow, telling you how to combine the error from multiple different elements when they're in one equation. And let me tell you, it's not as simple as just adding them all up. There are certain formulae that you have to use depending on whether there's addition or subtraction, multiplication or division or powers within your equation. And overall, this increases the amount of error that's going to be, that's there. So we have two sources of error. One from the regression equations in the form of prediction intervals, and one from the power equation itself in the form of error propagation. So the real question here is there too much error? Is there so much error associated with calculating an aerodynamic power curve using regression equations that they become completely unreliable? Well, in order to answer this question, I trawled through the internet trying to find as many regression equations as I could for both body mass, body frontal area, and wing area. From there, I calculated their prediction intervals and then tried to calculate a relative proportion of error so I could find the narrowest intervals possible. So I calculated this relative proportion of error as the percentage sum of difference, or percentage SD, between the upper prediction interval and the regression line. Using this value, I could get a relative width of the prediction interval, so then I could find the narrowest intervals with the least amount of error associated with them. Then I used these equations and the errors from the Then I used the errors from the prediction intervals and the errors from the propagation rules, combined them into the power equation, and then created some APCs. So let's go back to the APC for our mute swan. So this is the APC that I showed you earlier, and just as a quick recap, this is the APC, or the amount of power that the bird needs in order to fly at a certain speed, and this is the maximum power that it can actually produce. So this is our APC with our added errors onto it. And what I want to draw your attention to is the sheer amount of error present here. So this is the range within which an APC could actually lie. So that means that theoretically, our APC could lie all the way up here. Now, if our APC did lie up here, that would mean that our swan couldn't fly at all, which is a bit ridiculous, really. I mean, obviously, a swan can fly, right? However, we don't actually know that about the fossils, and that's where our issue is. So if this were the APC of, for example, I don't know, Archaeopteryx, then I wouldn't be able to tell you whether or not Archaeopteryx could even fly, never mind anything about its flight style. And before you say, this is actually the APC of a mute swan, not the APC of Archaeopteryx, I did actually create an APC for the 11th specimen of Archaeopteryx, and I pretty much got the same result. I mean, so the issue that we have really is this line all the way up here. So this is the maximum limit within which an APC could lie, and it is way above our maximum producible power line. However, there's something interesting here. If we compare the APC of the mute swan to the APC of Archaeopteryx, we can see something interesting if we take a look at the y-axis limits. Now, the y-axis limits show you the amount of power that the bird needs to produce. And what we can see is that for the mute swan, these y-axis limits vary between 0 and 800 watts, whereas for the Archaeopteryx specimen, they only vary between 0 and 200 watts. And that's to get a very similar looking curve. So I don't need to run a statistical analysis here to tell you that this is a very large difference. There's definitely a much smaller margin of error with the Archaeopteryx compared to the mute swan. Now, why would that be? In order to answer that question, let's go back to our power equation. So as I said before, body mass is squared. In contrast, neither body frontal area nor wing area have any power associated with them. So that means that any error associated with body mass is going to reflect significantly within the APC and is going to significantly affect the margin of error. And lo and behold, if we compare the weights of the mute swan to the weights of Archaeopteryx, our mute swan weighs well over 5 kilos, whereas the Archaeopteryx barely weighs 1 kilo. And this is reflected in our y-axis limits, which we're going to use as a proxy of the error margin. And basically, this massive difference in body mass is what's causing this line to be all the way up here, so far up ahead of the maximum available power. So this begs the question, if we find a small enough bird, can we produce an APC with a small enough error margin that the chart suddenly becomes reliable? Well, I took a look at several different specimens over various different ages, ranging from large to medium to small, all the way down to 15 grams. And I got the exact same result for every single one of them. For every single one of them, this line was way above this line. Nice and simple. Which, however, this is actually quite unfortunate because these things have so much potential actually to say things about flight style. It's just such a shame that the error margin is so large. So I guess, back to my question from earlier, is there too much error? Yes, just yes. There is way too much error associated with calculating an APC using regression equations. However, it's very easy to neglect these errors though, isn't it? I mean, I know from personal experience that I don't have much of a statistics background, and I wouldn't have known to even consider these errors before this study. And I guess this is a good point to thank my supervisor for showing me the error of my ways. So I guess what I'm trying to say is that this should really be a cautionary tale to everyone. No matter what analyses we do, we're all going to have some error associated with our calculations, and it's really, really important to take these into account. Because if we don't, then we might actually end up misinterpreting our results or coming to conclusions that we may not have come to otherwise. So, yeah, that's it. Are there any questions? Thank you.